In this video, I'll introduce capacitors, which are one type of electrical component that stores energy. Capacitor voltage-current relationships contain a derivative. This means that the equations governing circuits which contain capacitors will be differential equations. In this video, we'll start talking about energy storage, and I'll introduce our first electrical energy storage elements, capacitors. First, I'll go over some basic properties of energy. Energy is always the result of an integration. In more specific terms, energy is the time integral of power. Since energy is the result of integrating power, we can't change energy instantaneously without applying infinite power. Since infinite power isn't realistically available, that means that energy can never change instantaneously. As we'll see later in this video, capacitors store energy as voltage. We'll also see that the voltage across a capacitor can be determined by integrating the current through the capacitor. That means that a capacitor cannot change its voltage instantly. Since energy is the result of an integration, the equations governing energy storage are differential equations. Differential equations essentially govern the rate at which energy can be stored in a system. Physically, capacitors are constructed by separating two conductive materials with an electrical insulator. Electrical insulators, or dielectrics, don't conduct electricity. So when we apply a voltage difference between the two plates, positive charges build up on one plate and negative charges build up on the other. The separated charges create an electric field in the material between the plates. This electric field stores energy. The circuit symbol for a capacitor is shown here. A capacitor is a passive circuit element, since it can't create energy from outside the circuit. So we have to follow the passive sign convention when we assign capacitor voltages and currents. The capacitance of the capacitor is represented here as C. Capacitance have units of farads, which are represented by a capital F. The capacitance essentially indicates how much energy is stored in a capacitor for a given voltage. A capacitor with a larger capacitance stores more energy for a given voltage than a capacitor with a smaller capacitance. As with resistors, capacitors are modeled mathematically by the voltage-current relationship at their terminals. The IV characteristics for a capacitor is that the current is equal to the capacitance times the derivative of voltage with respect to time. An alternate formulation can be obtained by integrating both sides of this equation. So the capacitor voltage is equal to 1 over C times the integral of the current plus an integration constant that corresponds to the initial voltage across the capacitor. As an example of this, let's take a look at the current through a capacitor resulting from applying this voltage waveform to the capacitor. The current is the rate of change of voltage with time. So in this range between here and here, the current will be a positive constant. While the voltage is constant, the current will be zero, since the voltage change with respect to time is zero. Finally, in this range of time, the current will be a negative constant corresponding to the slope of this line. Notice that the current can change instantaneously, but the voltage cannot. Next, let's look at the voltage across a capacitor resulting from applying this current waveform to the capacitor. The voltage is the integral of the current, so in this time range the voltage will increase at a constant rate, since the area under the current waveform increases linearly. While the current is zero, the voltage remains constant, since the voltage change with time is zero. Finally, in this range of time, the area under the current curve is negative, so the rate of change of the voltage curve is a negative constant. Next, I'll look at some important consequences of the capacitor voltage-current relationship. First, if the voltage is constant, the current must be zero, since current is proportional to the time rate of change of the voltage. This means that if the capacitor voltage is constant, the capacitor behaves like an open circuit, which also allows zero current flow. A capacitor's voltage will become constant anytime a constant input, either an applied voltage or a current, is applied to the capacitor for a long time. This conclusion will help us determine the particular solution of differential equations with constant forcing functions, which I'll talk about in more detail in the next unit. A second effect of the voltage-current relationship has already been alluded to. In order for the voltage to change instantly, the current has to go to infinity. Since there's no such thing as an infinite current source, since that would require infinite power, we can't change a capacitor's voltage instantly. This property will help us with finding initial conditions on the differential equations we'll write and solve in the next unit. Now let's do an example of these properties of capacitors. In this circuit, the switch is at position A before t equals 0. At t equals 0, the switch instantaneously moves from position A to position B. We want to find the capacitor voltage, Vc, just before the switch moves at t equals 0 minus, just after the switch moves at time t equals 0 plus, and as t goes to infinity. At t equals 0 minus, the input is constant and has been constant for a long time. That means that at t equals 0 minus, the capacitor looks like an open circuit and there's no current flow through an open circuit. The appropriate circuit to analyze becomes this 6-volt source, a 2-ohm resistor, this other 2-ohm resistor, and finally the capacitor, which looks like an open circuit. The voltage we're interested in is V sub C at 0 minus. Since this current is 0, these two resistors are in series and this looks like a voltage divider. So Vc at 0 minus is 1/2 of 6 volts or 3 volts. The transition of the switch from point A to point B happens instantaneously, but the capacitor can't change its voltage instantaneously. So the voltage at t equals 0 plus is the same as at t equals 0 minus. After the switch moves, the capacitor is again connected to a constant source, and if I wait for a long time, the capacitor will again look like an open circuit. So as t goes to infinity, the capacitor looks like an open circuit. Its voltage is Vc at infinity. I have a resistor, 3 ohms, another 3 ohm resistor, and a 2 amp source. The current through here is 0. So this voltage is the same as the voltage across the 3 ohm resistor, and this entire 2 amp current goes through the 3 ohm resistor. So V sub C at infinity is 3 ohms times 2 amps, which is 6 volts. The voltage at t equals 0 plus is the initial condition on the differential equation that will model the capacitor voltage for all times t greater than 0. The process of the transition from its initial to its final value at t goes to infinity requires us to solve that differential equation, which we'll do later. Finally, I'll provide some additional support to my previous remark that the capacitor voltage dictates the energy stored by the capacitor. I'll start by reviewing power, which is the product of voltage and current. Since current is C times dV dt, the power is V times C times dV dt. By definition, energy is the time integral of power. If we integrate this expression, we find that energy is equal to 1/2 times C times V squared of t, evaluated at the limits of integration. If we assume the capacitor voltage is 0 at t goes to minus infinity, this means that the energy at any time is just 1/2 of the capacitance times the voltage squared at that time. So if you tell me what the capacitor's voltage is, I can tell you how much energy is stored by the capacitor. The voltage uniquely defines the capacitor energy. This is important since if we know the capacitor energy, we can find out anything else we need to know about a circuit containing that capacitor. The other type of electrical energy storage elements are inductors. Inductors are a dual element to capacitors. Voltage and current switch roles in the characteristics of inductors versus capacitors. I'll talk about inductors next.